everyone, this is Kalpana here. In this video, we are going to solve a differential equation from higher order linear differential equation. So let's get going. Problem. Solve d square plus 4 into y equals to x sine x. Firstly, let's find the order and degree of the given differential equation. Identify the highest derivative. Here d square is the highest derivative, so our order will be 2. And highest power of the highest derivative is the degree. Degree is 1. Or just write the given differential equation as d square y plus 4y equals to x sine x. We know that d is a differential operator. Then d square will be d square by dx square. Now we can write our equation as d square y by dx square plus 4y equals to x sine x. Here d square y by dx square is the highest derivative, so our will be 2. And highest power of the highest derivative is our degree. Degree is 1. Now coming to the problem. We are given a differential equation. D square plus 4 into y equals to x sine x, which is an operator form. F of d into y equals to q, right? Where f of d equals to d square plus 4 and q equals to x sine x. Now we need to find the general solution to the given equation, which is given by y equals to yc plus yp. We'll find yc using the roots of the auxiliary equation of the homogeneous equation of the given non-homogeneous equation. Simply by putting RHS to 0, we'll get the homogeneous equation of the given non-homogeneous equation, and we'll find yp using 1 by f of d into q. So I'll show you yp in two ways. Okay, we'll see two methods of finding yp. So let's begin with yc now. We are going to find yc using the auxiliary equation. The auxiliary equation of f of d into y equals to 0 is f of m equals to 0, where f of m equals to, we have f of d square plus 4, right? Let's replace differential operator with m, so that we'll get f of m equals to m square plus 4. Now the auxiliary equation becomes m square plus 4 equals to 0. We need to find roots here, right? Then m square equals to minus 4. Then m equals to plus or minus square root of minus 4. Now write this minus 4 as minus 1 into 4. Again, we can split the square root of minus 1 into 4 as square root of minus 1 into square root of 4. We know that square root of minus 1 is I and square root of 4 is 2. So we'll get plus or minus I into 2 or plus or minus 2i. Right? We got a pair of complex conjugate roots. Therefore, m equals to plus or minus 2i is a pair of complex conjugate roots of our auxiliary equation, right? We know that a plus ib is a complex number, then its conjugate is a minus ib. Likewise, if a minus ib is a complex number, its conjugate will be a plus ib, right? So we can call a plus or minus ib as a pair of complex conjugate. In case of m equals to a plus or minus ib, we'll get yc equals to e power ax into one constant into cos bx plus another constant into sin bx. Okay, but in our case a is 0, then we'll get a into 0, sorry, e power 0 into x, which is e power 0 into c1 cos bx plus c2 sin bx. Also we know that e power 0 is 1. Then we'll get 1 into c1 cos bx plus c2 sin bx, right? 1 into c1 cos bx plus c2 sin bx is c1 cos bx plus c2 sin bx. So we are going to use this to find our yc. Complementary function. Yc equals to, compare plus or minus 2i with plus or minus ib. Then for b equals to 2, we'll get c1 cos 2x plus c2 sin 2x. We got yc. Let's find yp. Okay, I'll show you in two ways. Particular integral. We'll find yp using 1 by f of d into q. We have f of d and q. F of d is d squared plus 4 and q is x sin x. Okay. So this is of 1 by f of d into x into v form, where v is a function of x, some function of x. Okay. Or I can write it as some better. So now, here we are having 1 by f of d into x into v, right? We use the formula 1 by f of d into x into v equals to x into 1 by f of d into v minus f dash of d by f of d whole square into v. Okay. Then this becomes x into 1 by f of d into v minus f dash of d. If f of d is d square plus 4, then f dash of d will be 2d plus 0. Just 2d, right? We'll get 2d by f of d whole square. D square plus 4 whole square into sin x. Again, this is of some 1 by function of d into sin bx form. Here also we are having sin bx. So we'll use 1 by some function of d into sin bx procedure here. Okay, this is d not 0. Then this becomes x into, I'll just write the same step, okay, for my convenience. And I'll write this as 2d into 1 by d square plus 4 whole square into sin x. This is of 1 by function of d into sin bx form, right? And here also we are going to use 1 by some function of d into sin bx form. Okay? Just forget about this square. Okay, we'll see that later. Now, compare sin x with sin bx. And for b equals to 1, we'll find d square, which is given by minus of b square, which is equals to minus of 1 square, which is equals to minus 1. So here, our d square is minus 1. Okay. Now let's see what happens if we replace d square with minus 1 in the denominator. Always remember that the denominator must be non-zero. What if denominator becomes 0? We'll just get this. This term becomes 1 by 0 into sin x, right? Since 1 by 0 is undefined, so total term becomes undefined. Okay. So the denominator must be non-zero. Let's see what happens if we replace d square with minus 1. We'll get 3, which is non-zero, right? We got non-zero by replacing d with minus 1. So what we'll do? This becomes x into 1 by, we'll just replace d square by minus 1. We'll get minus 1 plus 4 into sine x minus 2d into 1 by, replace d square with minus 1, we'll get minus 1 plus 4 whole square into sine x is equals to x into 1 by minus 1 plus 4 is 3 sine x minus 2d into 1 by minus 1 plus 3, plus 4 is 3 whole square into sine x, right? Then yp becomes x into 1 by 3. Okay, we can write x into 1 by 3 as x by 3 sine x minus 2d into 1 by 3 square is 9 sine x, right? This is equals to x by 3 sine x minus 2 into 1 by 9 into derivative of sine x, right? This is equals to x by 3 sine x minus 2 by 9 derivative. D is a differential operator, right? We can write it as d by dx of sine x is equals to x by 3 sine x minus 2 by 9 into derivative of sine x with respect to x is cos x. Now just take the LCM of 3 and 9. 3 ones are 3 threes are 3 into 3, 9. 9 is your LCM. So in the denominator first term we are having 3, so close 1 3 and multiply this 3 to x sine x, so you'll get 3x sine x minus, in the denominator of second term we are having 9, right? 3 to 3, 9. So we need nothing to multiply with 2 cos x. Just write 2 cos x is equals to, or you can just write it as 1 by 9 into 3x sine x minus 2 cos x, which is our required yp. Therefore, yp equals to 1 by 9 into 3x sine x minus 2 cos x, or 3x sine x minus 2 cos x by 9. Okay, I'll show you the another method to find yp. Yp equals to 1 by f of d into q. We have f of d 1 by, okay, f of d is d square plus 4 and q is x sine x. This of 1 by f of d into x power m into some v form, for v being sine x. Okay. Now, for m equals to 1, which is positive, okay, we'll use e power I theta. We know that e power I theta equals to cos theta plus I sine theta, right? This is a real part and this is a imaginary part. So, sine theta equals to imaginary part of e power I theta. We can say like that, right? Sine theta equals to imaginary part of e power I theta, and cos theta equals to real part of e power I theta, right? In our case, we are having sine x, so we'll use imaginary part of e power I theta. So we can write this as imaginary part of 1 by f of d into x into, we are just writing this sine x as imaginary part of e power I theta. For theta equals to x, we'll get e power I x here. Got it? Just replace theta with x, then we'll get cos x plus I sin x. So imaginary part will be sin x, right? Imaginary part of e power ix is sin x here. Right? Fine. Again, this of 1 by some function of d. This is again f of d, right? F of d itself. F of d into e power ax into some function of x, or let it be x. I'll write some v. Okay. This of 1 by f of d into e power ax into some v form. So what we can do here? We can just shift e power ax towards left by replacing d with d plus a. Right? So let's shift e power ix here by replacing this d with d plus I. Right? Just compare e power ax with e power ix. Then for a equals to I, we'll find d plus a, which is equals to d plus I. Now, let's shift e power ix. Imaginary part of e power ix into 1 by, replace this d with d plus I whole square plus 4 into x. That's it. This is equals to imaginary part of e power ix into 1 by, expand d plus I whole square, will get d square plus I square plus 2di plus 4 into x. Then yp becomes imaginary part of e power ix into 1 by d square plus I square, since I square equals to minus 1. So we'll get plus of minus 1 plus 2di plus 4 into x is equals to imaginary part of e power ix into 1 by d square plus into minus 1 plus 2di plus 4 into x is equals to imaginary part of e power ix into 1 by d square plus 2di plus 4 minus 1 is plus 3 into x. Now, this is of some 1 by function of d, some function of d into x power k form, right? We know how to solve this, right? This is equals to imaginary part of e power ix into, now we need to take the lowest degree term common from all these 3 terms. But in the first 2 terms, we don't have any 3. So what we'll do, we'll just multiply and divide 3 to the first 2 terms. Okay. Then it will be easy to take 3 common in the next step. This is equals to imaginary part of e power ix into 1 by, now take 3 common from the 2 terms of denominator. Then we'll get d square plus 2di by 3 plus 1 into x. You can write it as, just split this fraction as 1 by 3 into 1 by d square plus 2di by 3 plus 1 into x is equals to imaginary part of, I'll bring this towards left. Okay. 1 by 3 into imaginary part of e power ix into 1 by, we can write it as 1 plus d square plus 2di by 3 into x. See, this is of some 1 by 1 plus x form, so that we can write it as 1 plus x whole inverse, and we can use binomial series expansion. Okay. Before using binomial series expansion. Let's find the derivatives of x. Derivative of x is 1. D square of x is derivative of x is equals to, we have the value of derivative of x which is 1 and derivative of constant is 0, so we'll get 0. Likewise, so on. D cube of x, d power 4 of x, everything becomes 0, right? In general, d power k of x equals to 0 for k equals to 2, 3 and so on, right? Now keeping this in mind, we'll expand 1 plus x whole inverse. 1 plus x in the sense 1 plus d square plus 2d plus I by 3 is equals to 1 by 3 into imaginary part of e power ix into, we can write 1 by 1 plus x as 1 plus x whole inverse into x, right? This is of 1 by 1 plus x form, we can write it as 1 plus x whole inverse, right? We'll get d square plus 2d plus I here by 3. Now let's expand 1 plus d square plus 2di by 3 whole inverse. We know that 1 plus x whole inverse equals to 1 minus x plus x square minus x cube plus so on. Then let's expand for 1 plus d square plus 2di by 3 whole inverse is equals to 1 minus d square plus 2di by 3 plus d square plus 2di by 3 whole square minus plus and so on, right? We know that higher derivatives from d square is 0. Okay, higher derivatives of x from d square is 0. So we can neglect higher derivatives. We can write this as, just write as it is. Plus d square plus 2di whole square by 3 minus plus minus plus and so on, right? Let's see what happens if we expand d square plus 2di whole square. We'll get d square whole square, 2 2s are 4 plus 2di whole square is 4i square into d square plus 2 2s are 4, d square into d is d cube into I. So we got higher derivatives, d square, d cube, d power 4. Okay, we know that d square of x is 0, d cube of x is 0, d power 4 of x is 0. So from here we'll get higher derivatives. Okay, we'll get higher derivatives from here. So we'll neglect all the terms from here and we'll take only the first two terms. Okay, because we are getting higher derivatives. Now coming to yp, this is equals to 1 by 3 into imaginary part of e power ix into expansion of 1 plus x whole inverse is 1 minus d square plus 2di by 3 plus d square plus 2di by 3 whole square minus d square plus 2di by 3 whole cube plus so on into x. Since d power k of x is 0 for k equals to 2, 3 and so on, so neglect higher derivatives or higher derivative terms from d square, d cube and so on, right? So we'll neglect all the terms from here. Okay, so we'll get only the first two terms. This equals to 1 by 3 into imaginary part of e power ix into 1 minus d square plus 2di by 3 into x. Again we can write this as 1 by 3 into imaginary part of e power ix into 1 minus, I'll write this as minus d square by 3 or 1 by 3 into d square, minus into plus, minus 2 by 3 or I into 2 by 3 into d into x. This is equals to 1 by 3 into imaginary part of e power ix into 1. Okay, here we can neglect this d square term also, or we can just write like this. 1 into x is x minus 1 by 3 into d square of x minus I into 2 by 3 into d of x. Right? Now we are having the values of d square of x and d of x. Let's put it. We'll get x minus 1 by 3 into d square of x is 0 minus I into 2 by 3 into derivative of x is 1, which is equals to 1 by 3 into imaginary part of e power ix into x minus I into 2 by 3. Since we know that e power ix equals to cos x plus sin x, I sin x, right? Now replace e power ix with cos x plus I sin x. This is equals to 1 by 3 into imaginary part of, replace e power ix with cos x plus I sin x into x minus I into 2 by 3. Now we are going to multiply these two. This becomes 1 by 3 into imaginary part of cos x into x is x cos x plus into minus I into 2 by 3 into cos x is 2 by 3 cos x, right? Plus into plus I into x into sin x is x sin x plus into minus I into I square into 2 by 3 into sin x. Since I square is minus 1, so this becomes 1 by 3 into imaginary part of x cos x minus I into 2 by 3 cos x plus I x sin x minus of, replaces I square with minus 1. Okay? This becomes 1 by 3 into imaginary part of x cos x minus I into 2 by 3 cos x plus I x sin x minus into minus plus 1 into 2 by 3 is 2 by 3 sin x. Right? Now, identify the imaginary parts. I, term involving I. Okay? So, now, we have to pick the term involving only I. Okay? Term involving I. So, we have two terms involving I. So, I'll write this too. Imaginary part of these terms is minus 2 by 3 cos x plus x sin x. Right? We don't need real part. So, I'll cancel these two. Okay? We'll take only these two terms. This equals to 1 by 3 into minus 2 cos x by 3 plus x sin x. Now take the LCM of 3 and 1. Then this becomes 1 by 3 into LCM of 3 and 1 is 3. In the numerator you get minus 2 cos x plus 3x sin x. Right? Is equals to 1 by 3 into 3x sin x minus 2 cos x by 3, or we can split this fraction as 1 by 3 into 3x sin x minus 2 cos x, which is equals to 1 by 3, 3 is 9, into 3x sin x minus 2 cos x. Therefore, yp equals to 1 by 9 into 3x sin x minus 2 cos x. See, mostly we'll prefer the second method to find yp. Okay? To reduce the complexity, we'll just utilize the second method to find yp. Now let's go for the general solution because we got yc and yp. The general solution is given by y equals to yc plus yp. Then y equals to yc, c1 cos 2x plus c2 sin 2x, and yp is 1 by 9 into 3x sin x minus 2 cos x. This completes the problem. So we have seen a problem from higher order linear differential equations in this video. Hope you'll understand. We'll see you in the next video. Till then, bye bye.